All right, chemistry, it's day 63. We're going to be covering basic gas laws. This is May the 26th, and it's the first day of the 5th week of distance learning, so we're coming down the home stretch. Please get in any lessons that are any assignments that you haven't gotten in. Focus on days 33 through 53. Even if you could just get in some of them, get them in. The deadline for those is tonight, Tuesday night at midnight. So even if you can just do 3 or 4 or 5 of them that you haven't done, that'll make a big difference. And then get in the rest of the lessons this week and next week. Come to the Zoom meetings, by the way. You get 50 points extra credit. That's a lot of points just for showing up and saying hi. So I would take advantage of that. And just trying to give you as many ways to get through this class and even to get a good grade as I can. A lot of us, of course, just want to get through this school year. And so I'm trying to make it possible. But some of you I have not heard from, and I really need to get you going in these last 2 weeks. Okay, so what are gas laws? They are basically the physics of how a gas particle or gas molecule, atom, or particle behaves. In this unit, we're not dealing with chemical reactions, but we're dealing with basically the physics of how a particle moves around as a gas. So you think about when you throw a ball, some of the things you studied in physics. When you throw a ball, how the ball flies through the air, what kind of energy it has when it bounces off of a wall. That's really what the gas laws are about. And so we'll be talking about those for the rest of this week. So let's just review. Molecules have intermolecular forces that attract them. Some of them are very weak, like London dispersion forces, which nonpolar molecules have. Others, like water molecules, have dipole-dipole interactions. They have a positive-negative end that kind of acts like a magnet. They also have what are called hydrogen bond forces. And these are fairly weak forces compared to covalent ionic and metallic bonds. So if there's enough kinetic energy, which in simple terms means heat, to break apart those molecules, then they will break away from each other. And not only will they break away from each other, but they can actually defy the gravity of Earth and start flying up into the atmosphere. So if kinetic energy overwhelms the Coulombic attractions, those are the intermolecular forces, then the molecules separate and exist as gas or vapor. The study of gas laws treats atoms, molecules, or ions in gas state as though they are little balls. We don't care, in other words, about protons, neutrons, and electrons. Those are of interest when we're dealing with chemical reactions. But here we're just dealing with how do they behave physically. So since the gas can be either an atom, molecule, or ion, we use the generic term particle. So when you hear particle, it's just a way of saying atom, molecule, or ion, whatever the gas happens to be. So as you see these moving around, gas molecules will move randomly like this. The gas particles don't randomly change direction the way they appear to be doing here. You must imagine that these particles are changing direction because they are encountering other particles that you can't see, or the sides of a container. So you really have to kind of imagine that there's 100 of these little circles bouncing around, and they keep bouncing off of each other. That's what happens with a gas. But just to simplify the diagram, I just included 4. So they don't just naturally change directions. So this gives the appearance, though, when they bump into other gas molecules, it gives gas particles the appearance of a random motion. Gases can take part in chemical reactions. So I said we're not interested in that, but they can take part in chemical reactions. In fact, a lot of chemical reactions can only take place if the reactants are in a gas state. That's because they're moving fast enough to slam into each other and break apart and recombine into new substances. So the example that we've used often in this class for a basic chemical reaction is 2 H2 molecules plus 1 O2 molecule will combine to create 2 water molecules, either water vapor or water liquid. So water can be produced from hydrogen gas and oxygen gas. But in this unit, we're not interested in chemical reactions. We're just interested in how do they behave the same way a ball that you throw through the air would behave. So in this unit, we are only interested in how gas particles behave due to 4 factors. The first is pressure. That's the pressure of the atmosphere and ultimately the pressure of the gas. The second is the temperature of the atmosphere. The third is the volume of the container. And the fourth is the number of particles, which we measure in numbers of moles. So let's start with pressure. Think of pressure simply as how many times particles hit the side of a container. Technically, the definition of pressure is force divided by area. It's how much force you're putting on a certain area. But since the gas molecules of a particular type all contain the same amount of mass and the same velocity, we'll talk about that, then they're all hitting the sides with the same amount of force. And so the more often they hit the sides, the more force they're putting on the sides of the container, and therefore the more pressure they have. So volume is the amount of space the container occupies. So in some cases the volume can change. You can think of a balloon that can either inflate, get larger, or deflate, get smaller. Or you can think of a glass jar. In other cases the volume will be fixed. So that would be a fixed volume on the right. Temperature. Temperature is the average kinetic energy of gas particles. Now that definition's not quite as clear as to what that means. So let's review what kinetic energy is. So from physics, you may remember the formula that kinetic energy is given by the formula Ke, kinetic energy equals 1/2 mass times velocity squared. So by increasing temperature, what you're doing is increasing the kinetic energy, the average kinetic energy of the particles. Now, since the mass of the particles remains the same, for example, if you have a hydrogen molecule, it has a certain mass. It doesn't get bigger or smaller. That stays the same. Since it remains constant, then if you go up to that equation, and if you increase the Ke value, the only thing on the right side that can increase it, the mass is going to stay the same, is the velocity. So by increasing the kinetic energy, you increase the velocity, which is just the way of saying the speed of the particle. So therefore, increasing temperature increases kinetic energy, which increases the speed of the particles. Okay, so let's take an example here. Let's say we have particles of two different masses in a container at the same temperature. So it doesn't matter that one particle is heavier than the other. If they're at the same temperature, it means that they both have the same kinetic energy. So let's just pick some numbers and do a little thought experiment. Let's say the mass of particle A is 2 atomic mass units, and the mass of particle B is 8 atomic mass units. So particle B is 4 times more massive than particle A. And let's say the temperature is such that they both have a kinetic energy of 16 joules. So both particles have the same kinetic energy, 16 joules, so we can compute the velocity of each particle. So using the formula Ke equals 1/2 mv squared, for particle A, the kinetic energy is 16. That equals 1/2 times the mass of A, which is 2, times the velocity squared. And doing a little bit of algebra, you solve for the velocity of particle A and you get 4. It doesn't matter what the units of measure is, we'll just accept that number as 4. For particle B, it also has a kinetic energy of 16 joules. So 16 equals 1/2. The mass of B is 8 times the velocity of B squared. So if you solve for the velocity of B, you get 2. So what you can see is the velocity of A is twice the velocity of B. So the 2 AMU particle moves 2 times faster than the 8 AMU particle. So the 2 AMU particle moves 2 times faster than the 8 AMU particle. This leads to the following relationship for two gas particles called Graham's Law of Effusion. Effusion just roughly means how fast the particles are moving. We'll define it formally in the next couple of days. So the formula is this. The speed of the lighter particle compared to the heavier particle is equal to the mass of the heavier particle divided by the mass of the lighter particle, and then you take that number and take the square root of it. So in the example we just did, how many times faster is particle A, the lighter particle, than particle B, the heavier particle? So you put the mass of particle B on top, the mass of the lighter particle A on the bottom. 8 divided by 2 is 4. The square root of 4 is 2. So it gives us the same result we saw in the previous slide, that the lighter particle, particle A, moves twice as fast as the heavier particle, particle B. We don't know how fast that is. I mean, we don't know how many meters per second it is. All we know is that A is moving twice as fast as B. That's what Graham's Law of Effusion tells you. So temperature is the average kinetic energy of molecules. And this translates into meaning that higher temperature increases the speed of the molecules. So if you consider this to be a hydrogen molecule at standard room temperature, and then over on the right, you suddenly heat it up, you put a flame underneath it, you transfer heat in there, then the molecule starts moving like this. So it starts moving faster. You've kept the volume the same, and so the molecule, well, that doesn't really matter. The molecule is going to be moving faster if it's heated up. There's really only one major formula that relates the four variables of gases, and it's called the ideal gas law. And it's PV equals nRT, which is pressure times volume equals the number of moles times the gas constant R times the temperature. So PV, T, and N have been previously defined, so we know what those are. R is called the ideal gas constant, and the number it is specifically 0.0821 liters atmospheres over moles Kelvin. So the purpose of this constant is that it cancels the units of measurement properly so that only the units of the final answer appear. Let's say, for example, you're given volume, number of moles, and temperature, and you know the gas constant, and you're trying to calculate P. What the gas constant with all those different units of measure will do is it will cause all the units of volume, number of moles, and temperature to cancel out so that the only unit left at the end of the problem is atmospheres, the unit of pressure. So you can think of it, remember we did conversion factors when we did stoichiometry last week, how we got units to all cancel out and we were only left with the units at the end of the problem that we wanted in the final answer. Well, you can think of a gas constant as four different conversion factors all rolled into one number. So no matter what you're solving for, if you were solving for temperature and you were given pressure, volume, number of moles, it would make the pressure units of measure, the volume units of measure, and number of moles cancel out so that the only unit you were left with is the proper units for temperature. So it's really just one conversion factor created out of four different conversion factors. The other thing it tells you that's very important when you work problems, and I'll have you do some of these tomorrow, is it tells you what units you have to use. For example, for volume, you have to use liters. So if you're given milliliters in the problem, you have to convert to liters. For pressure, you have to use atmospheres. There are other units of pressure, torrs and pascals, but if you're given one of those, you have to convert it into atmospheres, otherwise the number won't work. For temperature, it has to be in Kelvin. Oftentimes you're given the temperature in centigrade, so you have to add that number to 273 so you have the temperature in Kelvin. So you always have to be sure that the units that you're working with in that equation are the proper units. All right, using the ideal gas law, PV equals nRT, we can see how any two variables relate to each other. Let's first define what we mean by an ideal gas. An ideal gas is a gas where the gas particles don't interfere with each other. They don't slow each other down, they don't break each other apart, they don't do anything to each other. So in addition, intermolecular forces between particles don't exist in an ideal gas, so particles don't want to stick together. So you can think of it like two billiard balls when you watch somebody playing pool. One of them just strikes another and immediately it clicks away and moves in another direction. That's basically what an ideal gas molecule is. When it hits another molecule, it doesn't slow it down, it doesn't change it in any way, it just bounces off and it keeps going. All right, now we're going to use the ideal gas law to compare two of these variables at a time. So what happens to pressure when volume is increased? So in blue are the variables, and in red are the ones that we're holding constant. So if nR and T remain constant, then as V increases, P decreases because the particle hits the side fewer times. Let's first look at the equation. You can just see mathematically that if you increase V and you want nRT to stay the same, then you're going to have to decrease the value of P appropriately so that P times V still equals nRT. So what this means is we have on the left, we have a particle, a hydrogen molecule, moving in a container of a certain volume. So what happens if we increase the volume? Well, the temperature is the same. That means these two molecules are going to be moving at the same speed, because you remember temperature basically tells you the speed of the molecule. It determines the speed of the molecule. So both of these molecules are moving at the same speed. But you can see the one on the right, it has a bigger volume to cover, and therefore, even though it's moving the same speed as the one on the left, it doesn't hit the sides of the container as many times. And remember, that's what we define pressure as being, is how many times does the particle hit the sides of the container. So because the particle on the right is in a bigger container, it won't hit the sides as often, and therefore increasing the volume lowers the pressure of the gas. The relationship between pressure and volume is called Boyle's law. Now let's examine the relationship between pressure and temperature. What happens to pressure when temperature is increased? So if you simply look at the equation, pressure and temperature are on opposite sides of the equal sign. So as one of them goes up, the other one has to go up by the same amount in order to keep the equation in balance. So if we hold nR and V constant, then as temperature increases, pressure increases because the particles hit the side more times. So here we have a particle at room temperature, and it's moving at a certain speed. And then we're going to increase the temperature, so we're going to put fire underneath the one on the right-hand side. And that particle, as we just saw, is going to move faster. So the particle's moving faster, and since the volume of the container is the same, it's hitting the sides more times than the one on the left. That means the pressure goes up. Pressure is how many times does the particle hit the sides of the container. So by increasing temperature, you increase the pressure inside the container. The relationship between pressure and temperature is called Gay-Lussac's law. Now, finally, the relationship between volume and temperature. So what happens to volume when temperature is increased? So there you see in the equation, since they're on opposite sides of the equal sign, that as one of them goes up, the other one has to go up. So if nR and P remain constant, then as temperature increases, volume increases. For the particle to hit the sides the same number of times, that is when there's constant pressure, that means the particles are hitting the sides the same number of times, while moving faster at higher temperature, the volume must get bigger. So let me get the other one going there. So in other words, these particles, if they're going to have the same pressure, by our definition of pressure, means they must be touching the sides the same number of times. And if you were to count, you would find that they're touching about 2 times per second. In both of the balloons are touching 2 times per second. So to have the same pressure, they have to be touching the same number of times per second. But since the one on the right is moving faster because it's being heated up, then the balloon must therefore be bigger. You're going to have to make that one travel a farther distance so that it's touching the same number of times as the particle in the smaller balloon. Okay, so for the particle to hit the sides the same number of times, which is constant pressure, while moving faster at a higher temperature, the volume must get bigger. And this is called Charles' law. And we have one more. That's pressure and number of moles. So the two of those are on opposite sides of the equal sign. So as one of them goes up, the other goes up. And this one is kind of easy to understand. If the temperature, gas constant, and volume remain constant, then as the number of moles, that is the number of particles inside that container, increases, the pressure increases very simply because there are more particles hitting the side. So if you only had one hydrogen molecule, it would have a certain pressure. If you put a second one in, that means molecules are hitting the side twice as often, so the pressure will be twice as much. If you put in a third one, the pressure would be 3 times as much because you'd have 3 times as many moles. So if T, R, and V remain constant, then the number of moles increases. P increases because there are more particles hitting the sides. The relationship between pressure and number of moles is called Avogadro's law. Okay, so that concludes the lecture for today. So no real problems to do, but just to understand the concepts, I'll give you some numeric problems to do tomorrow along with solutions. And please get in assignments. Try to get in 33 through 53 today, as many of those as you can. And I will see you tomorrow.